we start with where we left. So we were talking about kernelization or pre-processing, right? So I'll again write what are the I'll again write what we formally want, what we mean when we say we want a kernelization algorithm or a kernel, okay? So let's say I is an instance of a decision problem. We know that a parameterized problem is nothing but an instance of a decision problem and with a parameter p. So for example, for vertex cover, the decision problem, instance I will contain a graph G and an integer k, and depending upon what parameter we want to deal with for vertex cover, p will be that parameter. So for example, as I said, we'll mostly be working with parameter which is the solution size k, so here p will just be k. So I'm just writing this down formally so that the framework is clear that in general, in a general parameterized problem, what do we try to achieve in kernelization? Once I've written the general theme, then we'll just extract out what exactly do we need for our problem, okay? So given an instance I comma p, a kernelization algorithm is a polynomial time algorithm. So when I say polynomial time algorithm, meaning the running time is a polynomial function of I. I is the instance. So for example, for vertex cover, it will be a polynomial function of the graph, the number of vertices and the number of edges in the graph, and k. Okay. So a kernelization algorithm is a polynomial time algorithm that takes as input this instance IP of a problem and returns an equivalent instance of the same problem, let's say I prime p prime. So what does it mean to say that these instances are equivalent? So first of all, when I say these instances are equivalent, these should be instances of the same problem. By which I mean, if you are trying to solve vertex cover on instance I, you are here also you're trying to solve vertex cover on instance I prime. Okay, so okay. So what do I mean when I say equivalent? I mean if I is a yes instance. I is a yes instance, meaning we know we're talking about decision problems. So when you give an instance I as input, the answer will either be a yes or a no. So if the answer to this instance is yes, we say I is a yes instance. So if I is a yes instance for the problem, then I prime is a yes instance and the reverse also holds. If I prime is a no instance to the problem, then if I is a no instance to the problem, then I prime is a no instance. Okay, so this is what I mean when I say instances are equivalent. So suppose in polynomial time, starting from this instance, I can come up with an instance that is equivalent to this. Then observe that we have boiled down to solving the problem on this instance to solving the problem in this instance, because if this instance says no, if this instance says no, so look at the contrapositive of this, or in other words, if I was a yes instance, then this instance would say yes, and if I was a no instance, then this instance would say no. Or in other words, if at all this instance says yes, okay, look at the contrapositive of this statement then. The contrapositive of this is if I prime is a yes, then I is a yes. So if it indeed says yes, this is a yes, and similarly if this says no, it's a no, right? So we can forget about this instance now and talk about this instance. So in kernelization, starting from this instance, we want to get to an equivalent instance there with an additional property that the size of I prime is some function of p. So this is some function of p. It could be 2 power p, p square, any polynomial or exponential, any. We don't care at least. So if we are able to get to an instance I prime where f of p is a polynomial function, we say we have a polynomial kernel for this problem. And if this function is an exponential function, we say we have an exponential kernel for this problem. Okay. And also, just for technicalities, we want I prime to be f of p, and we also want p prime should be some function of p, we don't care. Like this is just so that we don't do any stupid things and create an instance where the parameter is insanely large, which most of the, like in most natural problems you won't do it, but just so that the definition is robust, we just write it down for formality, okay? So this is the definition of a kernelization algorithm. It takes as input of a parameterized problem, it returns an equivalent input instance with the property that these size bounds hold, okay? And as we saw, if suppose we have a kernelization algorithm for a problem, then we have an FPT algorithm for the problem, because we'll run this polynomial time procedure and then we can brute force over this instance and solve the problem, okay? So, in the last class I stopped at vertex cover. I said for vertex cover, I'll give you a polynomial time procedure that produces an equivalent instance where that instance is size k square, okay? But before even going there, let us look at some trivial kernels. What do I mean by trivial kernels? See here, basically ideally, for example, I was talking about pre-processing in the morning. Like you have a huge instance and you want to identify some irrelevant parts and throw them out. So that requires some work, right? Looking at what part really is irrelevant or not. But for some problems, you can actually achieve this thing, an equivalent instance which has small size, by in some sense doing nothing algorithmically, by just observing certain things. And I'll just talk about that first and then we'll go to vertex cover, because for vertex cover we actually have to make some effort to identify which parts of the graphs are irrelevant, and such that if I throw them, the instance remains equivalent and the size bound holds. So that requires a little bit of work, so we'll come to it. But before that, let us talk about some problems where, believe me, algorithmically we don't really have to do anything to get to such instances, okay? So for that, let us talk about this problem called max 3-sat. This is nothing but the decision version of the 3-sat problem, okay? I'll define it. So it takes as input a CNF formula, a 3 CNF formula psi over some n variables. So the CNF formula is of the form, let's say it has some m clauses, okay? It takes as input the CNF formula and a positive integer k, okay? And it outputs yes if there is an assignment to the variables here, which makes at least k clauses which satisfies at least k clauses. So for example, in the general optimization version of 3-sat, we want to find an assignment that satisfies all the clauses, right? So in the decision version, we have we also give as input an integer k. So you can give me an assignment that doesn't satisfy all the clauses, but it has to satisfy at least k of them. So clearly, when you put k equal to m, this is nothing but the original 3-sat problem, right? So there you want to satisfy all the m clauses. So again, what is it? It will output yes if there is an assignment to the variables that satisfy at least k clauses, okay? And it outputs no otherwise. So it outputs no when there is no assignment that satisfies at least k clauses, or in other words, every assignment satisfies at most strictly less than k clauses, okay? So this is the problem. And my claim is it in some sense has a very trivial kernel, and I'll tell you why I'm saying it has a trivial kernel, okay? For that, let us observe one thing, and this observation will directly lead us to a kernel for this problem. So the observation is the following, and let's see if one of you can come up with the proof, because it's very easy to prove it. I'm claiming that no matter what CNF formula you give me, okay, you can always find an assignment that satisfies at least half the clauses. I'll write it down and you can just think about it. So I'm saying let psi be a 3CNF formula. Then let this be any 3CNF formula, right? I'm not restricting it to be anything. Then there always exists an assignment that satisfies at least, so suppose it's a formula on M clauses, then there is always an assignment that satisfies at least half, so at least M/2 clauses. Any ideas on how you would go about doing it? So you understand what I mean when I say an assignment satisfy a clause, right? So when you assign the literals of that clause with respect to that assignment, that clause is a disjunction of literals, right? So that clause should evaluate to 1, right? So can you always, can someone tell me an assignment that will always satisfy M/2 clauses? Okay, I'll give you a starting hint. So start with any assignment that you like, any assignment, any arbitrary assignment to the clauses, okay? If it satisfies at least half the clauses, then you're happy. Any arbitrary assignment. If it doesn't, then what does it mean? You look at an assignment. So what is an assignment? So suppose the variables are x1, x2 to xn. So an assignment will be, it might assign this 0, this 1, 1, 1, 0, something like that, right? And this is the formula psi. So it is, so suppose you started with this assignment, and when you put this assignment in this formula, this didn't happen. So that means strictly less than M/2 clauses were satisfied. Or in other words, strictly greater than M/2 clauses were not satisfied. Then using this fact, can you come up with another assignment? He just pointed that out. Exactly. So if we just complement this assignment, if it was assigning x1 0, put it 1, and so on. Look at the clauses which this assignment was not satisfying. So that means, suppose this was a clause, some CI clause, and suppose it had, let's say it had these literals. If this was not satisfying this, that means it was making this 0, like this literal 0, this literal 0, this literal 0. Now if I take an assignment which is the complement of this will in fact make all these things 1. So whatever clauses were not satisfied by phi will be satisfied by the complement of phi, right? So just start with an arbitrary assignment, check how many clauses it satisfies. If it satisfies this, happy. Otherwise, just take the complement. It will definitely satisfy at least half the clauses. We have just made this observation. We have not done anything to the graph. So suppose you have this. Okay, so let me say, suppose you have this observation. Now suppose in the input instance, k was some number less than M/2. Then what can you say? So if k was at most n/2, then basically what is the question asking? It is asking, is there an assignment that makes at least k clauses true? So is there an assignment? No matter what instance it is, right? So note that I don't even have to look at the instance. I'll just look at the k value, see if it is at most M/2. If it is, I know it's a yes instance. So if suppose I was just giving an algorithm, in that case I'll just output yes. I would have outputted in polynomial time, but there is, yeah, I'll come to it later. So in this case, we know the input graph is a yes instance, or not the graph. The input instance is a yes instance. Otherwise, what do we have? So what does this mean? Sorry? What? It already satisfies what? Sorry? Yes, exactly. So if you, otherwise you are in this case, what does this mean? That means m is strictly less than 2k. That means in the input instance itself, the number of clauses were 2k. Or in other words, we are saying that then the input instance itself was bounded by the by this parameter. See, there's nothing fancy happening. It's just that it turns out that if the parameter value is small, then we can solve the problem. Otherwise, the parameter is large enough, quite large. It's almost the size of the instance, right? And in that case, all we are saying is then you return the whole instance, because then the whole instance itself has size bounded by the size of the parameter, right? So, okay, one more thing. If m is at most 2k, then what can we say about n? How many variables can there be in this instance? It's a 3-sat, 3CNF. Yeah, so every clause can have at most 3 variables, different variables. So n is at most 3 times m, right? Which is 6k. So, okay, another important thing is when we are designing a kernel, we have to argue that the size of the instance is small. So, when we have to argue the size of the instance is small, we have to argue, like for example, in this case, we have to argue that the number of clauses are small and the number of variables are small. Okay. So, in this case, definitely we have this. So, basically, what is it saying? It's saying that if this doesn't happen, then the input graph size is already bounded by the size of the parameter. In this case, what I'll do is, like the input instance was 5. In this case, I'll just return the same instance. Right? So let's see if I've satisfied the property. I wanted to give you a polynomial time algorithm. This is definitely a polynomial time algorithm because all we are doing is checking the value of k and doing something. It's a polynomial time algorithm, and given an instance, so the input instance was some phi, comma p here was k. So given an instance this, in this case for example, I'll be giving and I'll be outputting the same instance. Are these instances equivalent? Trivially, right? If they're the same instances. So this property is satisfied, they're equivalent. Is the size bound satisfied? The parameter is k. And what is the size of phi? So for the size of phi is like m and n, and I know m is at most 2k and n is at most 6k. So definitely the size of the output instance is bounded by k, right? So, okay. So, but there is just a small catch. So technically, if we were suppose giving an algorithm, an FPT algorithm for the problem, what we would do in this case is we would say yes, it's a yes instance, and in this case we would return this instance. And now because the size of this instance is small, we can just brute force over all possible assignments, right? To check if there is an assignment satisfying at least k clauses. Like there are only n variables. So how many possible assignments are there? Some 2 power 6k, right? So just brute force over all possible assignments, and in 2 power 6k time, you can decide if there is an assignment that satisfies this clause. So you can solve maxat in basically 2 power 6k time into some, like this is just a constant time procedure anyway, right? So you can solve maxat in this much time. So definitely max 3 sat is FPT. But for technical reasons, suppose I asked you to give me a kernel. I'm not interested in an FPT algorithm. So for technical reasons, I told you, okay, I have given you an instance. You have to output me an instance. Okay. So for this case, for example, if you check k is strictly greater than 2, you are outputting me an instance of the problem, right? So for example, by the definition of a kernelization algorithm, I give you an instance, you output me another instance with this property. Okay. But in this case, you're not outputting me an instance. You're just outputting me yes or no, right? But suppose if I was very strict and I said, okay, I've asked you for a kernelization algorithm and it asks you to output me an instance, so you have to output me some instance in this case, what could you do? But the instance should have size this, right? Its size should be bounded by the parameter. In this case, it's not guaranteed whether the size will be bounded by the parameter, right? But what I know here is that the instance, the input instance itself is a yes instance. So basically, so what is the property that I want? I want to output an equivalent instance of small size, right? Like, just think about it. Like, it's like how we cheat. Exactly. Just return an instance that is always true, and that's small, a trivial instance. For example, in this case, I'll output an instance where psi is a single clause, which is x1 or x2 or x3, and k is say 1. So you want to find an assignment that satisfies at least one clause. So this is always a yes instance, right? So in this case, I've output you an equivalent instance, and of course its size is small, right? So basically, if during kernelization you observe that, okay, in this case, it's always a yes instance or always a no instance, you can always create some trivial yes or no instance of constant size or of this case size and return that, okay? So for henceforth, whenever we conclude that in this case we can say yes or no, I'll just write yes or no, but for a kernelization algorithm, you can always think of some trivial instance to return. So again, note that and this is indeed a trivial kernel because we haven't really pre-processed. We just observe certain thing and we realize that if it is big, then I know it's a yes, and otherwise it's a small. It's the size of the input graph itself is small, and when I say small, it's bounded by the parameter. So if the parameter was small to begin with, the size will be small. Okay. So this is one example of a trivial kernel. Now we'll see another example, and I hope you guys will be able to guess it because Sunil has already refreshed the vocabulary which is needed for this. So let's try to solve the independent set problem, but not on general graphs, on planar graphs. And there's a reason that I'm not doing it for general graphs. One could be that the proof is very hard, but it's not that the proof is very hard. It's because that if I was able to give you a kernel for independent set on general graphs, I would earn $1 million or probably be shooted because people don't believe such a kernel would exist for this problem. I mean, we'll see some lower bounds in the last class, and let's see how much we will be able to cover it there, but that's for fact. So what we are doing right now is we are looking at this problem called planar, let's say, independent set. So what's an input? The input is a planar graph, okay? And so the input is a planar graph, and again, it's always a positive integer k, okay? And the output is, the algorithm outputs yes if G has an independent set of size k and no otherwise. So it's the standard independent set problem, but the input is now a planar graph, okay? So again, the parameter here is k, okay? So let's see, what can you say for independent set? See, again, the kind of ideas that you want to come up with is, okay, if suppose we can say that, okay, a planar graph always has this, at least this much independent set, then we can always return yes, and otherwise something of this sort. Okay, do we have some lower bound on the size of an independent set in a planar graph? Like here we had a lower bound that any assignment will satisfy at least m/2 clauses, right? So if you say that, okay, any independent set in planar graphs will have size at least something, then probably we can try to use that fact. Sorry? You've learned
maximum chromatin number in planar
is what?
6.
Yes.
So we can do that.
Okay, so let's go by that. So this is an easy proof, right? That I think you've learned about planar graphs, right? Lavanya taught you. Have you guys seen a proof of like the chromatic number of a planar graph is 6? It's easy. Did you see it in the class? Yes or no? Okay. So let me just tell you, and I'll briefly tell you the proof of this also, probably later. So in a planar graph, this is a fact that the chromatic, if G is a planar graph, then the chromatic number of G is at most 6. Actually, it's at most 4, but the proof of it is it's non-trivial. But the proof of 6 is what you can see easily. So it doesn't matter what we choose. So suppose I tell you this, then you were saying something. Then what can we say? Then do we have any lower bound on the size of the independent set? So, okay, what does it mean that a graph has chromatic number 6, as Sunil was just teaching you? How can you alternatively look at a graph with chromatic number 6? If the chromatic number of the graph is 6, so look at this coloring using 6 colors and look at each color class. So this is all the vertices that get color 1, all the vertices that get color 2, and so on, all the vertices that get color 6. Each of this color class is an independent set, right? Then now what can you say about the size of can we say that such a graph will always have an independent set of certain size? Okay, n by 6 is okay, right? Pigeonholing. So there are n vertices. They've been divided into six classes. Of course, one of the class has to have at least n by 6 vertices, and each color class is an independent set. So any planar graph we know has independent set in any planar graph. If G is a planar graph, then G always have an independent set of size at least n by 6, right? Now this is basically an analogous observation to this, and after that what we will do, the same sort of strategy, what will you do? What is less than n by 6? K, right. So if I'll just go check K, if K is at most n by 6, so if you're looking, if your goal is to come up with an independent set whose size is at most n by 6, then I know I can always give you an independent set of this much size. So in this case, I can always say, otherwise, K is greater than n by 6 or n is 6K, right? And this is of course a kernel, but this only bounds the number of vertices. Can you bound the number of edges? Yes. So if in a planar graph you always have this bound that m is at most 3n minus 6. So if n, can you see this? No. So what we had was independent set of the graph is at least n by 6. From there we said that okay, if K was at most n by 6, then say yes. Otherwise, K is greater than n by 6, that means n is at most 6K. And in planar graphs, basically you have this bound that m, the number of edges in a planar graph, is always at most 3n by 6. So this gives us a bound on the number of edges also. So again, this is a trivial kernel, we don't really have to do anything. So while we are here, I would want to ask you a question. So how did we come up with this independent set? We said, okay, look at the 6 coloring of the graph, and look at the 6 coloring of the graph and look at the maximum size of the independent set, and that will have size at least n by 6. Okay, but when I'm designing a kernel, do I really have to go look at the coloring of the graph? Like, okay, or in other words, what is this polynomial time algorithm doing? What will this polynomial time algorithm do? Will it go first compute the coloring of the graph and then do something, or can it avoid computing the coloring of the graph and just conclude something? Exactly the point. So see, we looked at the coloring for our to observe that this is always the case, right? No matter what planar graph you give me, this is always the case. That's all we use the coloring for. the preprocessing algorithm will not go compute the coloring. It will just go check if k is at most n by 6, it will say yes. Otherwise, it will output the same instance. Because this is for a fact, like, so this is the difference between an existential argument and a constructive argument. All we want to say is that there is always an independent set of this much size. I'm not asking you to give me an independent set of that much size. There is always this, so hence I can conclude this. F of p, yes, I agree. So what am I returning? I look at two cases. Either k is this or it is this. If it is this, I return a trivial yes instance. So what could be a trivial yes instance? Just take a graph on one vertex. It is planar, and ask if it has an independent set of size 1. It has 1. So that's a trivial yes instance. So in this case, I'll return that instance. In this case, what am I returning? The same instance. And we just argued that the original instance itself has size bounded by a function of k. And the same instance is of course an equivalent instance because I'm returning the same instance, right? So I mean this is exactly what we did in Max 3 stat, right? So it just turns out that if the parameter, try to look at intuitively what is happening. What is happening is we are saying if the parameter value was smaller than the size of the input, if it was much smaller, in that case we know, so basically what is this saying? In other words, it's saying that the graph has a lot of vertices and the parameter is very small, okay? So in that case, if I had to come up with an equivalent graph, like I had to throw away a lot of vertices to get to an equivalent graph which has size bounded by this k, right? But this observation saves me to do all this preprocessing. This observation is just saying, okay, if this is the case, then you don't even have to look at the graph. You know it's a yes. So I just saved that there. This thing is nothing but, what is this saying? It's saying if the parameter is not small, then the parameter is big. Big as in the parameter is as big as the size of the graph almost. So or in other words, the graph size is bounded by the parameter because the parameter is so large. So we can as well return the whole graph. So note that of course in this case, if k was a big number, then what we are returning is a big number. But again, as we said in parameterized algorithms, our goal is to return, like in kernelization, our goal is to return an instance which has size bounded by the parameter. Now depending upon what parameter you give in the input instance, this will either be it'll either be a really small kernel or just a small kernel to say. Right? I mean that's what we saw in the morning when we gave a 2 power x into polynomial time algorithm. We said for instances that have small x values, you actually get a polynomial algorithm. But there might be instances that come with large x values. All I know is the running time is 2 power x into polynomial in n. Like it's bad, we know that, but I mean, and we can't hope to get good algorithms for all the instances because we're working with NP-hard problems. So now we'll quickly do the vertex covered kernel as we promised. So there we actually have to design some preprocessing, some real preprocessing, and get a kernel.